Okay, welcome to the Condensed Matter seminar. Today we're happy to have Hitesh Changlani visiting us from Florida State University. Hitesh got his PhD at Cornell, working with somebody who's very famous in frustrated magnetism circles. I think should be more famous and broadly in physics, the late Chris Henley. Then following a nice PhD working on some interesting frustrated magnetism problems, he moved to Urbana for a postdoc, continuing to work on some frustrated magnetism and then sort of more broadly some strongly correlated problems in general. And then he came to Johns Hopkins for a postdoc where we met, and Hitesh did some very nice work on some frustrated magnets there, including some work with me. And then he moved on to professor at Florida State University, where he's now associate professor, working on non-equilibrium systems as well as frustrated magnetism. So it's kind of a unique research program in that aspect that it combines these two pretty exciting areas of physics. So Hitesh, we're very happy to have you.
Thank you for the introduction and thank you for coming. So I don't know if I think this is small room, I'm audible, right? I'm loud enough, okay. And there are a lot of students, so the first part of my talk is going to be somewhat pedagogical. Hopefully there's something for everyone in it. And then maybe later on it gets a little bit technical, but I'll try to keep it as general as possible. And I'll use this if needed. And each of these pictures is not just there for decoration. It has a precise meaning in my talk, and I will explain what these images mean. Okay, so in case I'm rushing towards the end of the talk, let me just thank my collaborators right away. Some of you know Kyungmin. I think was telling me that he and Kyungmin overlapped at Cornell. So Kyungmin was my postdoc and now making real money at Samsung. And Arijit Pal is a professor at University College London. And my student Ron Melendres also did a lot of simulations in this work. And he's moved to Johns Hopkins Applied Physics Lab. But a lot of the core ideas that this talk is about were developed much earlier and applied much later. So those ideas were developed with Eduardo Fratkin, Brian Clark, and Dima Kochkov, who are the three people shown there. Okay, so there's a long backstory, and I want to develop the story and get to those two papers that I mentioned. Okay, so if a graduate student comes to my office and says, what do you work on? I always show them this slide. It's very easy to motivate what I work on. Everyone knows solid, liquid, gas, but when it comes to phases of electrons, it's a horribly complicated problem. There are phases there on these phase diagrams that we have been looking at, staring at for many, many years. And for lack of better names, we give them names like strange metal, simply because we don't know, it looks strange to us. And there are people in this department who have contributed to various aspects of these phases. So in that sense, we do have an overlap with a lot of activity that is going on here. And the two sort of people who inspire me in some sense are Walter Kohn, who said, look, we got to worry about all the electrons. We got to do, if you want to explain some material, we got to worry about, the details. Chemistry matters. I know I'm talking in the physics department, but chemistry does matter. And so sometimes I will put a thinking hat on where the details of the material are important if you want to understand some phenomena. And sometimes you got to think like P.W. Anderson. I know it's very difficult to think like him, but we'll try. Which is that we will focus on the core key idea, which is work with toy models, simplified descriptions of very complicated problems, in the hope that we can understand the essence of what is going on. So a lot of today's talk is actually in the P.W. Anderson style, but we don't shirk away from thinking like Walter Kohn when that's saying a lot. Okay, so those series of plots that I showed you had temperature and pressure, or temperature and doping, but it had a very important axis that was missing, which is time. How do these phases know that they have to go somewhere, or how do they know that, oh, I want to be a strange metal, I want to be a Fermi liquid. So given a set of initial conditions, how does the system navigate and become the phase that it does become? And that's where the axis of time comes in. Typically in condensed matter, we assume that things relax very quickly. Okay? You start from anywhere in phase space, and it immediately becomes a superconductor, or immediately becomes a strange metal. And we don't really worry about the relaxation mechanisms for how this happens. And yet, we know that non-equilibrium physics is all around us. Our own existence is a non-equilibrium process, right? We're a very complicated non-equilibrium being, not in equilibrium with our environment, fortunately. So people have, in the recent past, leveraged this idea to manipulate states of matter, or to realize states of matter that could not be normally realized in some situation. So to give you an example, if you consider a very famous model of strongly correlated electrons, which is called the Hilbert model. Some students may have seen this. Actually, there is a prediction from C and Yang back in 1989 that it can realize metastable state of matter, which gives you the Cooper pairing, the same Cooper who unfortunately passed away recently. So that was called the eta pairing state. And that just remained an idea in the realm of ideas, but Andrea Cavallari's group has recently, over the last few years, shown some evidence that if you shine light, you can excite your ground state to this metastable state, which is a long-lived state, and can realize high temperature superconductivity. The superconductivity that we're talking about is of the order of 20 Kelvin, and the evidence is a little indirect. Can't do a direct resistance measurement, so it's all pump probe experiments that are being done. But it at least entertains the idea that there may be phases of matter that cannot be achieved in normal conditions, but if you excite the system, you provide energy, or you apply a magnetic field, something could change. Hopefully there are some long-lived states, metastable states living in the spectrum that maybe you can steer the system toward. Today's talk is far more grounded than achieving that aim, because as theorists, we have to admit that a lot of the tools that we have are not yet ready to address this kind of question yet. So I'm going to be asking some simpler questions, in the sense that if I give you a configuration of electrons, I give you a configuration of spins, magnets doing something initially, and I ask how do their time evolve, do they reach some sort of thermal equilibrium? And what does thermal equilibrium even mean if these electrons are isolated from everything else in the universe? What is the whole idea of temperature? And can you even think in something like a canonical, non-canonical ensemble if you don't have the idea of temperature? So those kind of conceptual questions are motivated by lots of experiments that were just done down the road in Boston. So like in the Rydberg atom setup that is being realized in Lukin's group. And there have been other close parallel efforts working with cold atoms, ultra-cold atoms in Wolfgang Ketterle and Marcus Greiner's group, which we also look at very carefully. And finally, how can I not talk about quantum information? There is a lot of people at IBM and Google who are interested in benchmarking their noisy machines versus quantum dynamics, versus quantum dynamics that you can do on classical computers. So from that perspective as well, simulating the dynamics of electrons in different situations is a useful objective, just to see how good these machines are. So, right. So everything that I mentioned was mostly about electrons, but I'm going to be focusing mostly on the magnetic degrees of freedom, which are the spins. And it turns out that not only graduate students and professors are frustrated, it is also nature that is frustrated. And it appears a lot. You see that, for example, if you just take an Ising model, many of you may have seen, the students, and you consider an antiferromagnetic case, and you put two spins that are anti-aligned, the third one is not sure what to do, that's frustration for you. And that's a very toy description. but it actually frequently occurs in nature. And so one particular geometry that you're going to be looking at a lot is the kagome geometry. And there are actual minerals which have this structure. And you might wonder, oh, it's two-dimensional. Well, it's actually, there's a buffer layer of zinc. So it's a three-dimensional structure, but effectively two-dimensional. So it's not one of those Moire kind of systems that Lioli studies here in the department, which are also have this element of frustration. And frustration can do various interesting things. For example, you can stabilize different kinds of Wigner crystals. You can escape Nagaka's theorem for ferromagnetism, and you can sort of try out many things which do not happen, or you can stabilize many phases of matter which would not have normally stabilized for unfrustrated matter. And a lot of people think that 2D is the only place where frustration can be interesting, and Kemp and I guess, we differ. We think that three-dimensional physics is also very interesting. So there is a set of systems that we study which are pyroclores, and turns out that when you view these pyroclores along a certain axis, they also have this kagome motif appearing. So it looks like a kagome stacked on a triangle, another kagome stacked on a triangle. And so this kagome motif appears pretty universally in what we do. It's not the only interesting frustrated magnet, but it's one of those very, very interesting ones. So let's look at the physics 101 of frustrated magnets. Right? And let's not try to be very ambitious to begin with, and just ask ourselves, take a very simple Hamiltonian. Take the Heisenberg Hamiltonian. Everyone in the lattice students probably have seen this at some point. And ask yourself, forget about quantum mechanics. Okay, so then you can say, well, why is it interesting? We'll get to that. And just ask, what are the classical ground states of the Heisenberg Hamiltonian? And you can see that the Heisenberg Hamiltonian SI dot Sj, yes, I could have another equation there. It can be written as, if I just have nearest neighbor interactions, it can be written as Si plus Sj plus Sk squared up to some constants. And classically, the only objective I have now is to minimize the sum of three spins on every triangle. If I can do that, I have found a ground state of the problem. Now you can say, how many ways can you do that, or how can you do that? Well, I'm giving you one set of ways of doing it. Is that on every triangle you put a up arrow and an arrow at 120 and another arrow at minus 120. And so instead of working with arrows, I'm a little clumsy with arrows, I'll just call these three states as colors, red, blue, and green. And look, we don't have quantum mechanics, so we just need the sum of three spins to be zero. Vector sum of three spins to be zero. So I just need to put one red, one blue, and one green motif on every triangle. Whether it's an up triangle or a down triangle, I need to satisfy that. So let's look at this one. You have red, blue, green, red, blue, green, red, blue, green, red, blue, green. Every up triangle is the same pattern. And if you think of its modulation, just think of its wavelength as infinity. So there's a name given to it. It's just a name. It's called the Q equal to 0 phase. And then there's another phase there, or there's another configuration there, which is that you see the up triangles. It's green, red, blue, blue, green, red, blue, green. And it repeats, but it has a bigger unit cell of repetition. Turns out that that cell is √3 times √3, the size of the original cell. So that's why it's given a name √3 by √3 state. Now you ask, are these the only two states that you can construct which satisfy the 120-degree rule or the three coloring rule? Right? So that's where the name coloring is coming in. And the answer is no. So look at this one. You have red, blue, red, blue, red, blue, and think of periodic boundary conditions. That's what we theorists like to do, right? And imagine changing a red to a blue, blue to a red, red to a blue, blue to a red. Well, they're shielded by the greens, right? They're shielded by green, which means I am still satisfying the 120-degree rule. I'm still satisfying the three coloring rule, even though I have changed a red to a blue, blue to a red, and red to a blue. I have just changed the two colors on one of the loops. I can do that here as well. I can change red to blue, blue to red, red to blue. And that, again, is shielded by the greens in the sense that every triangle, whether it be up triangle or down triangle, is perfectly happy. So you can play this game. That's what Baxter did in the 1970s. Not quite on the kagome lattice, but something dual to the kagome lattice, which is called the honeycomb lattice. And he basically counted how many states there are. How many ways can you three-color the links of a honeycomb lattice? And links of the honeycomb is dual to the kagome, but essentially the problem maps, one problem maps onto the other. And the answer is that there are exponentially many ways of doing it. There's not only two ways, there's not only two plus, what I drew there. There's actually exponentially many ways of solving the classical problem with this three-coloring constraint.
Can I ask a question?
Yes, good.
So are these two have the same energy?
Yes, they have the same energy because the energy is just Si plus Sj plus Sk square up to some constants, and both of them minimize that Si plus Sj plus Sk square classically. Classically, they have exactly the same energy because they both satisfy the 120-degree rule or the three-coloring. So it's at the classical level, yes.
So you have infinite number
Yes.
of arrangements
Yes.
that all have exactly the same energy.
Absolutely, right. Yes. You have infinitely many, infinite with system size. Yes. Did I lose the, okay, what happened here? Okay, it's back. That's right, it's infinite. That is the, yes, and it has a very precise exponent. That's what Baxter calculated, was something like 1.208 to the power of n. Right, so it's not 2 to the n, it's 1.208 to the power of n. And then on the kagome, it's 1.13 to the power of n. So it's exponential, so smaller exponential, but it's exponential. Questions? So that's actually a key feature. And then you can ask, okay, what does quantum mechanics do? And I'll get to that a little later. But even the classical problem, there's a lot going on. Okay, and that's not the end of the story. As I said, Kemp and I actually are interested in the three-dimensional version of the kagome, which is pyrochlore. And you might say, well, it's just a counting problem. Sure it is, but it has observable consequences on experiments. I'll get to that as well. But here in the case of spin ice, now you don't quite have a three-coloring rule because now you have four guys, you have four sides of a tetrahedron, but you have a 2-in, 2-out rule, and that gives you a different exponent, that gives you a different counting. That's attributed to Pauling. Pauling did the version of this problem for water ice. So we kind of transferred this idea to magnetic ice. But the idea is that it is still exponential. And you can see impact of it in things like the specific heat. So for example, you can say if there was no entropy of these ground states, if you just had a unique state, the entropy should integrate to log 2 because you have two spin, you spin half per side. But actually it does not integrate to log 2. When you look at the entropy as a function of temperature, you see a residual entropy, which is pretty observable and big. That was seen by Ramirez, Kava, and Shastri way back. And that is substantial. That is actually, you actually see the impact of this degeneracy in thermodynamic everyday sort of measurements. Now, I just want to emphasize that this version of frustration, or this version of frustrated magnets that I'm going to be talking about, is sort of in a different class of frustration. You've seen the Nobel Prize given to Parisi a few years ago. And also for Hopfield neural networks, which are based on classical spin glasses, which are all-to-all interactions. They have disorder in them. But in this version of frustration, we're going to mostly consider simple Hamiltonians, no disorder, and yet there's a lot going on. Right? There's a lot of classical degeneracy going on, and you can ask, yes, go ahead.
If we go back to the previous model,
Yes, yes.
if you calculate theoretically
Yes.
the CV and S as
Yes,
function of
you will see a
temperature, what do you
residual
get?
entropy. Yes, you will see a residual entropy.
No, what do I expect to see? If you calculated the,
Yeah, you will see
the
residual
specific heat as
entropy.
function of temperature.
Yes, you will see residual entropy associated with the degeneracy of these states. Now, the thing is that in the Ising, it's discrete, and here it's a continuous, so it's not exactly, you don't have any, in the case of the discrete, you know that the specific heat should integrate to log 2. But if it's continuous, you're not allowing discrete spins, right? You're allowing spins to be continuous. Then there's no reason classically that the specific heat has to go to 0 at 0 temperature.
Theoretically,
Theoretically.
if you calculate the specific
Yeah.
heat, do the same plot,
Yes.
what do you get?
I don't know the answer. I should know the answer to that question, but I don't. Yes. Yes.
But that problem has
Yeah,
been around for a
classical,
long-
yeah, because
for a
I'm going to
long
go on to
time,
the
right?
quantum problem, but you're right. I mean, but it doesn't have to go, it doesn't, because it's a continuous of possibilities, because the spins can be continuous.
Or you say that has not been calculated?
Probably has, I just don't know the answer. Yes. Okay, no, thank you for the question. So I'm going to the quantum problem, but it's good that you're asking about the classical problem. Okay, so now you can ask, what does quantum mechanics do? Okay, you have all this classical degeneracy, and you can ask, what does quantum mechanics do? And so we already know from benzene, for example, if you have, you can have a resonance between structures, and so the structure is neither this nor this. That's what Pauling told us. And Anderson took that idea further and said, well, imagine that you can have a dimer covering. So again, it's a very quantum mechanical way of thinking that you can have entangled spins, up, down, minus, down, up. But if you go back to the coloring language, you can say, oh, there are many coloring states, and can you form some sort of superposition of colorings that doesn't resemble any of the colorings, individually. And so that idea has been sort of pushed by many people in the community, and people are looking for states of matter which are superpositions of many, many classically competing configurations. And the sum can be very different from the individual parts, and that is what is interesting, and I'll tell you why. Because, for example, if you shoot a neutron, the sort of experiments Kemp and I are interested in, Kemp actually does it, I just look at it. So if you shoot a neutron on a ferromagnet, you basically create two domain walls, and you basically create a spin flip, and the spin flip basically coherently propagates. That's what is called a magnon. And if you do it in an antiferromagnet, you get two domain walls, and these domain walls can proliferate independently. And so that's like, you have two spin-ons. You have, these domain walls essentially moving independently in this background of up and down spins. But actually, this idea is not only confined to one dimension, even though that's where a lot of these ideas originated. One can also push this for higher dimensional systems, like in spin ice, where you flip a spin and then you create two defect tetrahedra. So here you created two domain walls, but these defect tetrahedra can be moved apart. And some people like to map it to models of electromagnetism and call it monopoles. But in the spin language, it's just making the spins, these defect tetrahedra, deconfined. Okay, so people are looking for this kind of phase in the quantum mechanical world. And this is a program that Kemp and I overlap on. And you can actually see observable consequences of this in experiments. This is all equilibrium response, and this is where, as Kemp mentioned early on, this is where I started off. So if you have, for example, a 1D antiferromagnetic chain, but you put a large magnetic field, and you basically you study the neutron response, which means you look for spin waves, you see a quadratic dispersion. But if you look at it just in zero field, you actually see the remnant of antiferromagnet spin waves, but it's not quite spin waves, because I just told you that you create these two domain walls, you create these spin-ons. So actually, energy and momentum can be distributed, and so you see evidence of fractionalization in the neutron response, and you look for something like a continuum of excitations. So it's a very indirect measure, but that's about the best we have, given the probes that we are trying to model. And so we have been looking for signatures of the continuum in spin 1 pyrochlores, in spin orbit coupled systems with cesium. And this is more of an advertisement that we have approximate numerical methods which can basically address these problems in equilibrium and try to make meaningful comparisons between what we are seeing in experiment and what we are seeing in theory. But it doesn't involve any non-equilibrium as such. We're using standard Kubo formalism, Green Kubo formulas, etc. And we are able to model a lot of things that people in neutron scattering can see.
Okay.
Yes.
So I try to understand that
Yeah.
how do you go from
Yes.
classical to quantum? So
Yes, good question. Very good. That
okay,
was
so-
developed. That was the paper with Kemp that we. Yes.
So
Yes.
in the standard
Yes.
way we think about a quantum system, we have
Yes.
if the system has two degenerate states,
Yes.
and then I'm going to be in superposition of the two states, then the standard perturbation theory tells me then I'm going to form in this bonding and anti-bonding state if it's a single particle. But if for many body
Right.
system,
Yeah.
what's the consequence of that?
That's a good question. So the thing is, everything I showed you was a cartoon,
Yes.
and the cartoon is realizing is based off some assumption of what is going on.
Yes.
But I want to make as minimal assumptions as I can and try to let the computer decide, okay, this is what is happening, and then I'll interpret the data. And so this comes to my next slide, that to get an unbiased answer very often requires a lot of computation, for example. So there are techniques that we use.
Whoa,
which
one
are-
second. You
yeah.
didn't answer the question.
I
So
think
the
I did, yes.
system,
Yes, sorry, go ahead.
in,
I'll go
in
back.
quantum mechanics,
Yes.
the system spontaneously lift up the degeneracy, right?
Yes.
By just have a superposition.
Correct.
Here, how does it do it?
Spontaneously lifts up the degeneracy? Yes, because I'm actually going to. So these are purely quantum mechanical calculations. You cannot get this effect in classical mechanics. That is what I was trying to say. This is a purely quantum mechanical effect. This continuum of excitations is not a classical effect because I just gave it. See, okay, maybe I misunderstood your question. Once I flip once a neutron flips a spin.
Can you go back 2 more slides?
Yeah,
to
sure.
the-
Right.
Okay.
Yeah.
So if discounted all the infinite other many possible arrangement, if this
Yeah.
were the only 2
Correct.
degenerate states,
Yes.
and then if I do quantum mechanics, the
Yes.
system is going to be in superposition of the 2, right?
Not necessarily, because I
Yeah,
mean,
it has to.
perturbation. But it could be a very weak mixture of one versus the other. I mean,
No. Let's do the simplest.
Yeah, because it's a many. They differ in many. You see that they differ in many. So you also need a matrix element that takes you from state 1 to state 2.
Yeah,
Like
yeah,
a
yeah.
perturbation has to mix the states for you to have.
I understand. So,
I mean, it doesn't
but-
mix all of them. I mean, okay, it might mix.
but the new state, the 2 eigenstate, is
Yeah.
going to be neither of this, right? It's going to be.
But it could be predominantly this with very little mixture of this. In fact, almost no mixture of this, because if you have like a 2-body perturbation, it's not going to mix things that differ by so many spins. I mean, it can only connect you to only so many spins. You'll have to go to very high order perturbation theory to mix a lot of things in.
So degeneracy can always spontaneously be lifted, right?
Sure, I am not denying that, but there are situations where it is not. That is the whole point. And in fact, so the thing that was the standard law in the field is what is called quantum order by disorder, which means that if you look at every classical configuration and you ask, okay, I'll add a little bit of quantum mechanics by, let's say, choosing 1 over s as a small parameter. Just imagine, right? I do spin wave theory on each one of them. And I ask, there's some reduction of energy, free energy reduction about each one of those classical states, and I take the one that shows the most free energy reduction. Then that is the winner. But it turns out that that's not the complete story. That is not the complete story. And and yeah, I'm going to bring up something that will make it even more apparent. So anyway, the point is, I was just trying to say is that to address your question, sometimes we don't know what to do, and sometimes we have to rely on high performance computing. So we use algorithms such as density matrix renormalization to matrix product states. And a very simple way to appeal to a larger audience is, suppose I wanted to save the picture of Mona Lisa on a computer, I could save a very pixelated version of it, simply because there's so much information of it that I do not need for doing a practical calculation. And so the matrix product state, the DMRG wave function based ideas, they operate by condensing a humongous amount of information in quantum many-body wave functions into much smaller amount of information. So I can talk about this for another half an hour, but I won't. I just want to say that we use sophisticated computer algorithms to do the dynamical evolution of spins. And sometimes the algorithms are not sophisticated. Sometimes we still use, classical Monte Carlo, Landau-Lifshitz dynamics, etc., to create the kind of images that you see here. But basically, it depends on what energy scale you're interested in, what time scales you're interested in, what sort of accuracy you're interested in. But we basically do a lot of computation to address exactly what you said, that we don't think necessarily perturbatively. We sort of think of the strongly correlated problem as, okay, we have a Hamiltonian and we got to do its time evolution. And that requires to think beyond perturbation theory very often. And these numerical methods allow us to think in that. So this is an example of something. And I was hoping I could speak to Brad Marston here, because this is the kagome problem, and it's a quantum mechanical version, which has a 30+ long year history. Right? It's a very, very old problem, and people thought about this for a very, very long time. So in fact, very early on, such Dave and White-Elzer and also Claire Louvillier, I should have mentioned, actually thought that it's a spin liquid. And then Brad Marston and Rajiv Singh and others argued that it should be what is called a valence bond solid, which is exactly, it's really the difference between, is something like a solid, we're talking about an electron solid, we're talking about a solid of dimers, or is it like a liquid which doesn't show any dimer-dimer correlations. And I'm just condensing 30+ years on one slide, but if I have to summarize the state of the art right now, you see that the energy difference between what we believe is the liquid-like state, whose nature is still somewhat controversial, is lower than the valence bond solid, but not by a whole lot. It's 0.002 on a scale of J, 0.002 J. And if you ask what is J in these materials, it's about 200 Kelvin. So it's a very small scale. It's about 0.4 MeV, which, talk to any practical DFT person, is essentially zero, because that's the accuracy that we have on the Hamiltonian of the material in some sense. But it's been one of those things, like, people thought that this kagome realizes a spin liquid, but it's not quite definitively nailed down, even though we have very, very large scale state-of-the-art numerics that address this question. So you can say, what were we doing if 30+ years and some very famous people were working on this? What did we do?
Good question.
Right? Yes, go ahead. Yes.
So Brad's
this is Brad Marston.
that valence bond solid is very easy to understand, because that's essentially, if you consider two electrons, this is the covalent bond, right? So
but you need a 36-side unit cell. It's not just because of the nature of the kagome, because you cannot completely dimer cover the
that
kagome.
can be understood just from straight out of perturbation theory in quantum mechanics. But here, you say somehow they do not form this bond state.
They don't. Or it's a resonating. I mean, you can say it's bound, but it's a superposition of many such resonating bonds. And it's not just, it's not a, you see, if you could dimer cover everything, then the system might want to, but it's not, there are some incomplete dimers here, just because of the nature of the kagome, right? So it's not as trivial as that, and Brad did some very nice work back in 91, so a while ago. But I just want to highlight and connect it to the picture that I was talking about, which is that, what did we do? So we are theorists, and we play a lot with the space of Hamiltonians. As I said, we just took the liberty to change the Heisenberg Hamiltonian to XXZ, and I intentionally put not a very polished plot, because this is what I showed to one of my supervisors, and I was like, oh, what's going on here? If I change the ratio of JZ to JXY, and I take the liberty of making it unrealistic, you say, oh, in a realistic material, JZ and JXY are comparable, because it's Heisenberg-like, and you don't have much spin-orbit coupling. But I made it very unphysical, so I say, and we'll clarify what unphysical means. So I made JZ as ferromagnetic, and JXY to be antiferromagnetic. So let's take that to be 1, and let's take that to be -½ in some units, in units of JXY, sorry. You can also put a magnetic field if you like. There was a very nice looking number that we got. And the number turned out to be exactly -J, and I really meant JXY. So it was a very nice number, minus j divided by 4. And it looks like we're looking at a critical point, and we started to wonder what's going on here. Is a quantum critical point? Is something that we understand to the left of it, and there's probably something to the right of it that we would like to understand. But what is happening at exactly that point? Okay, so that was the puzzle, and the answer was the following: that everything I told you in the classical context for these three coloring states now has an exact quantum mechanical analog. What do I mean by that? I mean that if I take this value of jz equal to minus half j, j is jxy, there is an exact solution or exact ground state solution for any of these lattices. So any lattice of corner sharing triangles or any lattice of triangles that can be three colored, and there are many of them in the literature. I showed you some of them in the past. So whether it be sawtooth, triangle, kagome, hyperkagome, lots of them. If they can be three colored, they have an exact ground state at this value. Okay, so what's going on? Before we do something complicated, let's try to understand something simple. And so here it is a little bit technical, I apologize, but not very technical. Instead of looking at many, many triangles, just look at a single triangle. And in the single triangle, if you set not the Heisenberg point, but you go to the xy limit, the j is equal to minus half limit, you see that there are six-fold degenerate states here. You can ask what those are. And then you see two-fold degenerate states up in the spectrum, and their energies are minus 3j by 8 and plus 9j by 8. And it's a little bit of exercise in quantum mechanics, literally a few lines. You can convince yourself that these six states are basically the ferromagnet and the chiral state. So you have three spins, and you can basically take omega, which is e to the I2 pi by 3, and this is e to the I4 pi by 3, and you can do different chiralities. So you can think of one magnon going on a three-side loop, either this way or this way, right? You think of a three-side loop as having some momentum. Think of a particle jumping on a three-side loop. It has either momentum e to the plus 2 pi by 3 or minus 2 pi by 3, or it's a ferromagnet, and you take its Kramer's pairs. So up, up, up becomes down, down, down. That's allowed as well because the Hamiltonian is time inverse symmetric. So those six states are basically these three and the Kramer's pairs. And these two states have momentum zero. So you see they have up, up, down, down, up, down, up, down, up, up. They have no momentum. So they are momentum zero states. So the two high energy states are momentum zero. The lowest six are have non-zero momentum, or they are ferromagnetic. And I can just write the Hamiltonian in what we call a projector construction form, but basically it's just ket psi bra psi, something that you learned in quantum mechanics 101, and times the energy. Now, actually, this is a very old idea, but apparently was not appreciated for, and I'm very pleased that Professor Kostelitz is in the audience, because a lot of these projector constructions are the basis of the AKLT Hamiltonian, which was cited in the Nobel lecture, or in the Nobel Prize write-up for Haldane's spin one chain. There was a time when people were not so convinced that the spin one chain has a gap, and then AKLT wrote down a non-Heisenberg, Heisenberg plus biquadratic term, which has a gap, provably, because it has an exact ground state. But actually, the projector construction idea is older than that. So Majumdar and Ghosh wrote down one of the simplest 1D projector construction Hamiltonians for a spin half chain well before the spin one chain. And a lot of the GitHub, toric code, etc. models are also can be thought of as some projector construction, except that the projectors come out. Don't mean to make it too technical, but all I'm trying to say is that the Hamiltonian is the sum of triangular pieces, and each part can be written as a positive definite projector, which just involves these non-chiral states, these states which have momentum zero, and a constant, which is innocuous. I can shift everything by 1 million electron volts. It doesn't matter. Only energy differences matter in any observable quantity.
It is for the special JZ.
Yes. This is for the special JZ. It doesn't work for others. Right.
the chiral states break time reversal symmetry?
So they break time reversal in the sense, yes. I mean, if you have to complex conjugate this, but the thing is that there's a degenerate state. So yes, you would under time reversal you would flip up or down and change the omega to omega bar, omega square. So yes, they do.
And so here
Yes.
the expression is also for the special JZ.
This is all for special JZ. This is because for the Heisenberg, this doesn't look like this. The ferromagnet goes all the way up.
What's the correction to this special form when you slightly shift JZ from the special value?
So you asked a very important question because that's exactly what we pursued, but we pursued numerically. But what will happen is, sorry, yeah. So this ferromagnet. So if you consider the Heisenberg limit, these ferromagnetic states go up and become part of the multiplier because you have to have a SU2 symmetric multiplier for. So the thing is that these shift, but you still have a 4-fold degeneracy left, even in the Heisenberg limit. And in fact, throughout the XY limit, you have a 4-fold degeneracy. You have the spin and the pseudo spin. So you have two S equal to half kind of multipliers always in. So
I get, in the Heisenberg limit, I get degeneracy because I classify everything according to the total speed, right?
correct. That's
So
right.
in here too, because
Yeah,
you
so you have two,
you
because
always
you don't
have,
have
you always have rotation around the z-axis.
That's right. Yes, you have U1 here. You don't have SU2.
But for the corrections to the Hamiltonians, and
So you will have a term which is like a Jz plus half times, because you will have a correction, and Jz plus half, and that will couple to, I believe it will couple to, yeah, okay, good question. It will couple to not this state, because it's not just a multiple of this. So it will change this six-fold degeneracy, because this six-fold will now
so
become.
the high energy states would not be affected.
The high energy states won't be affected, but these two will start to go towards the high energy.
I wonder, but then if you flip your model, say you change the temperature to the negative temperature, then you don't need special value of Jz, you still see these two particle,
Correct.
two state
Yeah.
multiplet, and you can solve the system exactly for any Jz.
I didn't quite understand the question.
So
Can
you
say
will
that
be
again?
able to solve your problem exactly for any Jz if you flip the sign of the temperature.
I mean, if you flip J, you have a ferromagnetic model.
Oh,
you
that's
have
not interesting.
We know that you're going to get
that's not
ferromagnetism.
Yes, nothing interesting.
I won't say it's not interesting, but yes. And kind of you've anticipated what I was going to say next, because now all I was going to say, and I'm just formalizing what I just said, is that you can define the quantum mechanical equivalent, which I just call colors, but they're really just rotated spins. So this is like the spin in the x direction, and this is, you just put the omega here. So these are just coherent spins, and I'm just defining it as red, blue, green, or ABC. And the thing is that if you take a product of these three, it exactly serves as the exact solution of the projector Hamiltonian. So the projector Hamiltonian zeroes out, or is the projector annihilates these states. You just take a tensor product of these three. So everything I said in the classical picture, which was, you might say, oh, that was classical. But if you tune the JZ, then you can map the classical problem exactly to quantum mechanical problem. And everything I said in the classical context is valid. So now we have a quantum mechanical model, which has a large degeneracy that Baxter mentioned, except that it's, of course, a critical point. And now you can ask what happens if you perturb this critical point, as Dima was mentioning.
Can I ask another question?
Yes.
Is there any hidden symmetries that's responsible for that degeneracy?
Good question. And we are going to get to the idea of how this Hilbert space of these colors fragments. So it's not very obvious to me. Fragments means, I'll make it a little bit clearer. If you just wait a little bit, hopefully that becomes clear. And if not, I will, we can talk more. So just bear with me a little bit here. So how much time do I have? 15 minutes. Okay. So let me get to the main point, which is that if I consider, for example, in large phase space, where now I look at this critical point where I have the exact solution, and I perturb, let's say, as Dima was suggesting, I perturb in JZ, and this, okay, and I can also add second nearest neighbor interactions, which I call J2. Then, as I said, this is a highly degenerate point, and this is a line that I might care about, because okay, sure, there's an exact solution here. I should say exact solution with reservation, and exact ground state solution. But these projector constructions don't always work for excited states, because okay, and this is the Heisenberg limit that Brad Marston and others were studying. And so this is, I would say, the most controversial line here, or the controversial points here, which is the Heisenberg limit, which is most isotropic. But actually, even using perturbation theory, we can just perturb it a little bit in these directions. So you can, for example, make J2 negative, which is second nearest neighbor interaction, or J2 positive, or Jz negative. A lot of these ordered phases very naturally emerge both from our numerics and from analytic arguments. Right? So you perturb a little bit, you favor Q equal to 0 state, or you favor root 3 by root 3. But what is not clear to us, and where I would say we need the numerics, is that when we perturb a little bit towards Jz positive, we see a wide region, which is actually not so wide, it's a small region in J2 space, where we see signature of a spin liquid. And unfortunately, the numerics cannot resolve very small energy scales. I already sort of motivated that earlier. But at least it gives us some understanding of why this problem is difficult and where these ordered states that people saw previously in the Heisenberg regime emerge from. And they emerge from this multi-critical point, which we discovered during the course of our investigation. And now you can say, oh, this model is so crazy, why do I care about it? And at some point, I also had this feeling that this model is not so relevant to actual experiments or real materials. And I have been proven wrong. So there is recent work from some of my ex-collaborators, Suzy Zhang and also Oleg Chernyshov, Leon Balance. Experiments were done with neutrons, so Peng-Cheng Dai, where they actually considered or they found a cerium-based triangular lattice magnet. They subjected it to magnetic fields. They did neutron response. It's not a kagome system. It's a triangular system, but it's not a Heisenberg system. Rather, if you look at the parameters they derived or they fitted to, the Jz is negative. The J perpendicular, which was my J, is positive. And the ratio of Jz by J perpendicular is minus 0.43 with a pretty generous error bar. So I would say they located close to this multi-critical point, which is pretty close to the exactly solvable point. It's not the kagome lattice, but it's a triangular lattice. But the essential projector construction idea still holds. And so we are very impressed that something like this, which was just in the realm of theoretical possibility, can actually be realized in a real material. And we're trying to understand this this paper a little better. So it was just from last month.
What is the meaning of the notation magnesium/aluminum?
Right. So in this one, they have the cerium, which is the magnetic ion, and then they have presumably some sort of disorder that.
So it's not a crystal, so magnesium.
No, it's a crystal of the
places.
cerium. The cerium. So the thing is, see, magnesium and aluminum, they have very little spin-orbit coupling. You need strong spin-orbit coupling to have such a large anisotropy. So these are effective pseudo-spin models that are realized in cerium-based compounds.
But cerium atoms must interact, and so
Yes.
this interaction goes through whatever atoms are in between.
Sure, but the picture, or at least my understanding of their story, is that the interactions are primarily in plane, which is the triangular. That was my understanding.
So this.
But this is
molecule
pretty
is
fresh,
planes.
just from last month, so please don't quote me.
I see. So
But
the
this is
interaction
the-
goes through oxygens.
Yes.
I see.
Yes. Yes. And also, again, coming back to the realm of unphysical models, which are not so unphysical, Wolfgang Kettel's group has actually realized, they call it Heisenberg, but they really actually realize an XXZ model with tunable anisotropy, so that's delta. And these are not multidimensional, but they have plans to go to 2D. And yeah, but this is a one-dimensional version of this problem, where again you see the three coloring state, which is just a spin helix state, like ABC, ABC. And what they are doing is they are initializing spins.
This is an optical lattice.
This is an optical lattice, it's lithium-based, ultra-cold. And what they're doing is they're initializing spins, so they can address spins on an individual level. And they can ask, given this particular configuration of spins, at what rate do they relax? and which I have not spoken about at all. But the thing is that if the relaxation rate is very, very slow, that's basically telling you that these are eigenstates of your Hamiltonian. And that's what is happening. I mean, you don't see the relaxation rate or the decay constant going to 0. But that's what they're seeing. Essentially, they're seeing a dip corresponding to this particular ordering wave vector, which is 2 pi by 3. Which brings us to the question, how do these things evolve in time? And we need a lot more concepts to understand time evolution. But I will just give you a brief summary of what we are doing with the time evolution of these spins. So I told you something about the eigenstate properties, but you know from quantum mechanics 101, if you know something about the eigenstates, you can time evolve according to e to the minus I ht and tell something about what happens in the long time limit. And so, of course, I spoke about this ingredient. I didn't really address this yet. But there are people in the field who have told us that, and there is good evidence now, that if you have an isolated quantum system, which is not in contact with anything in the universe, and it's isolated, you can still define the concept of temperature. You can say, oh, I learned in StatMech, how can that be true? Well, the thing is that the system can serve as its own, the majority of the system can serve as a heat bath for the subsystem. And the subsystem looks at the rest of the spins and says, okay, I can thermalize in some effective background of these spins. So this might seem a little bit technical, but what this really means, and I'm just getting to the main point here, is that if I have a system start somewhere in this space, Hilbert space, that's what we quantum mechanics people want to think about, Hilbert space. And if you consider just 2 states in your Hilbert space, yeah, you're going to see oscillations of the memory function, which is given the name Loschmidt echo, which just tells you what is the time-dependent wave function and what is its overlap with the initial state. So, but if the phase space is very big, you will, if you have only 2 states, you just go back and forth and you see oscillations in this function. But if the phase space is very big, and I just chose some random matrices to communicate from points, but if the phase space is very big, and 20 is not a very big number, but you see it starts to decay towards 0, but there's still some remnant oscillations. And if you take 100, not spins, but just 100 states, 100 Hilbert space, so you just take a 100 by 100 random matrix, and you diagonalize it, and you ask, what is this time-dependent function? You see that the system has lost memory of where it came from. So generally, if you have a quantum system, and you say, okay, let it relax, it will lose track of where it came from. And these thermalization times are typically very, very fast, of the order of picosecond or smaller for condensed matter systems. But there was an experiment done, as I said, in Boston, in Lupin's group, where they cannot quite plot the memory function, so they look at some observable, which is basically tells you how many domain walls they have. So they don't really think in the spin language, but it's a 2-level system. And the key idea is that the relaxation of spins, maps to a spin model, but not quite, is actually oscillatory and does not decay, right? It doesn't decay to its steady state value right away. It oscillates significantly before it decays. The reason you can see this effect is because this time scale is of the order of microsecond, which is experimentally detectable. But it is very different from something going exponentially to some steady state value. So this became a subject of a lot of investigation. People were very interested in why this is happening. And that's where we came in as well. And we start to ask the question that can this athermal relaxation of spins or athermal relaxation of electrons happen more generically? So can you have certain states of the quantum many-body system which when you initialize, relax slowly, and when you initialize them to something else, relax quickly. So eigenstate thermalization would tell you, okay, if you have a typical state, it relaxes quickly and you're done. Right? And that's what typically happens in majority of the materials or majority of situations. But there are situations where this does not happen, and that has given rise to a very big field, which is not a complete list, but people are looking for quantum many-body star states. So, yes, go ahead.
As long as your system is finite size, shouldn't that have some sort of a recurrence?
Yes, yes. So the idea was that they did it for 9 and 51 atoms, but sure, they could have.
So the recurrence is pretty high.
Yes,
And
that's what they're
that's
saying. Yes, yes. Because even in my 100-state system, I mean, there's always something, like some oscillator. The thing is, does it survive in the thermodynamic limit or not? That is the question. That is the key question.
Also, okay.
So it is really a question about large system sizes, because you're right, on any finite system, you're going to have it. So let me just get to the main idea, and I think I will end the talk there, which is that we asked, can we also see, instead of seeing this decay, like they do over a long time, can we see perfect revivals? Can we have a perfect revival of states? And instead of having 1 or 2 states which violate ETH, can we have exponentially many states violate? So it cannot be all the states in the spectrum are violating ETH, but can we have many, many states violating ETH? And the answer comes back to our model of frustration, which is that we can try to make each one of these states an eigenstate of the many-body problem, because they have the same energy. Now, they wouldn't have the same energy in usual situations when you had Heisenberg interactions. But when you have this funny interaction that we discovered, which now turns out to have some other experimental relevance as well, we can make these exactly degenerate. And not only these two, we can make exponentially many states exactly degenerate. So we showed a proof of concept that you can have exponentially many 3-coloring states, which you can embed in the many-body spectrum. And if you initialize the wave function to those states, you can get these revivals, as long as you put a magnetic field. So you need a magnetic field term to split the U1, to split the SE degeneracy. So we did that, and just to get to the main result. So here is our expected, we also knew this analytically, but we also did the numerics. And here is, again, our Loschmidt function, our Loschmidt echo function for the 3-coloring states. So we chose one representative state here. But you can see that the revivals are perfect. So we did like 2 system sizes here. We chose the Q equal to 0, 3-coloring state. That was the state with these topological sort of winding loops. Once again, you can see that the revivals in the on-site expectation values of a spin are perfect. If you choose another state that is at the same energy, and if it is at the same energy, but it is not a 3-coloring state, you see that the decay is exponential. And it's so fast that you can't even really see it on this time scale that we plotted. But it basically quickly approaches the steady state value of 0. So as a proof of concept, we showed that there are exponentially many states. I don't think I have time to talk about this. I don't know, do I have a couple of minutes? Or maybe not. So I think I should end. And I should just conclude with saying one more thing, that this 3-coloring space that I introduced you to, hopefully I made it somewhat relevant. It has a very rich structure. These √3 by √3 states, actually, they have a lot of friends, in the sense that when you do quantum dynamics, they are very easy to flip. Whereas these guys, they have very long winding loops, so they are very difficult to flip. And that has an important consequence in dynamics, which is that if you look at these Q equal to 0 states, they relax. Sorry, I'm moving over a little. If you look at the Q equal to 0 states, they relax very slowly, or they don't relax at all. I mean, this is just some phenomenological model we had. And if you look at the √3 by √3 states, they relax very quickly. And these are just the 2 extremes. There's a whole family of relaxation times that we can get in this model. And so we are very intrigued by all these findings. And we have some qualitative explanation of it. But I should end here, and I should just say that, thank you for your attention. And we are, I think, just getting started with understanding a lot of things about how magnets respond in different situations. What we explored was the dependence on the initial state and the magnetic fields, etc. But I think there's a lot more to be done. So thank you for your time and attention.